vehicle's cooling system is simultaneously the most critical system for engine survival and the most neglected system in regular maintenance. Engines generate enough heat to melt their own components within minutes if cooling fails. Yet most drivers never think about cooling system maintenance until overheating occurs, by which point expensive damage has already happened. The catastrophic failures that total engines, the head gasket replacements costing thousands, the warped cylinder heads requiring complete rebuilds, all result from cooling system neglect that simple preventive maintenance would have completely avoided. I've diagnosed thousands of cooling system failures over 30 years. The overwhelming majority weren't caused by defective parts or unavoidable wear. They resulted from contaminated coolant eating aluminum components, air pockets preventing circulation, scale buildup restricting flow, and simple maintenance neglect allowing small problems to become catastrophic failures. Every single one was preventable through procedures so simple and inexpensive that most people can't believe they work as well as they do. Today, I'm revealing the complete cooling system maintenance protocol that makes radiators, water pumps, thermostats, and hoses last the entire life of your vehicle. Not just extending their service life, making them essentially permanent through prevention of every failure mode that normally destroys these components. This isn't theoretical. This is proven through vehicles I've maintained personally reaching 300,000 miles without any cooling system repairs beyond the regular maintenance procedures I'm about to teach you. The foundation of cooling system longevity is coolant chemistry maintenance through regular complete system flushes with proper procedure. Most people think changing coolant means draining the radiator and refilling. That removes maybe 40% of the old coolant, leaving 60% of contaminated fluid with depleted additives and accumulated corrosion products. This partial replacement provides minimal benefit while creating a false sense that maintenance was performed. The complete flush procedure that actually removes all old coolant and contaminants requires multiple cycles using a specific methodology. Start by draining the radiator completely through the petcock at the bottom. But don't stop there. Locate and remove the engine block drain plugs, typically found on the lower sides of the engine block. These drains release coolant trapped in the engine that the radiator drain can't reach. With all drains open, allow complete drainage for 30 minutes. Gravity pulls coolant from passages throughout the system, but only if you provide adequate time. Quick 5-minute drains leave significant coolant trapped in the heater core, engine passages, and radiator tubes. The 30-minute drain ensures maximum old coolant removal before introducing fresh fluid. After complete drainage, reinstall all drain plugs and fill the system with distilled water only. Start the engine and bring it to operating temperature with the heater on maximum. Run for 15 minutes at operating temperature, allowing the water to circulate and dissolve accumulated scale and contamination. Shut down and drain completely while hot. The hot water carries away contaminants that cold flushing misses. Repeat the distilled water flush cycle a minimum of 2 times, 3 times if the water drains visibly contaminated. Each cycle removes more residual contamination until the water drains clear, indicating the system is truly clean. Only then should you introduce fresh coolant, ensuring it works in a contaminated-free environment. Mix coolant with distilled water in a separate container before adding to the vehicle. Never use tap water. The minerals in tap water create exactly the scale deposits you're trying to prevent. The 50-50 coolant to distilled water ratio is critical. More coolant doesn't provide better protection. It actually reduces heat transfer efficiency and can damage components. Less coolant reduces freeze protection and boil-over protection. 50-50 is the engineered optimum. Add the premixed coolant slowly, allowing air to escape as the fluid fills the system. Modern cooling systems have complex passages, and air can become trapped easily, creating pockets that prevent proper circulation and cause local overheating. Fill to the proper level at both the radiator and overflow reservoir. Start the engine and monitor temperature while checking for leaks at all drain points. The thermostat replacement that should accompany every coolant flush is preventive maintenance that costs $15 in parts but prevents catastrophic overheating from thermostat failure. Thermostats are wear items that degrade gradually from heat cycling and coolant exposure. They stick partially open, causing slow warm-up and poor fuel economy, or stick closed, causing overheating that destroys engines. Replace the thermostat every 60,000 miles, regardless of whether it's failed or showing symptoms. The $20 in parts plus 1 hour of labor every 60,000 miles prevents the $3,000 to $8,000 engine damage that thermostat failure causes. This is the definition of cost-effective preventive maintenance. Install the correct temperature-rated thermostat for your vehicle. Manufacturers specify thermostat opening temperatures ranging from 180 to 205 degrees based on engine design and emissions requirements. Using a thermostat rated incorrectly creates problems. Too cold delays warm-up and increases emissions. Too hot stresses components and reduces longevity. Match the factory specification exactly. The radiator cap replacement that mechanics never recommend deserves attention because cap failure causes problems that mechanics love to misdiagnose as expensive component failures. Radiator caps maintain system pressure, typically 15 to 18 psi, that raises coolant boiling point and improves cooling efficiency. The cap's pressure relief valve and vacuum valve enable the overflow reservoir system to function. Radiator cap springs weaken from heat cycling and pressure cycling over years of use. The weakened spring reduces system pressure, lowering boiling point and allowing coolant to boil prematurely under high load conditions. The boiling creates air pockets that cause local overheating and engine damage. Mechanics diagnose head gasket failure from the symptoms when the actual problem was a $7 radiator cap. Replace the radiator cap every 2 years or 40,000 miles as preventive maintenance. The cap costs $7 to $15 and takes 10 seconds to install. This trivial maintenance prevents problems that cost thousands to repair. Buy quality OEM caps, not cheap aftermarket caps that fail quickly. The pressure rating must match factory specification exactly. The cooling system additive that transforms coolant protection comes from manufacturers' own formulations that aren't included in retail coolant but are added to factory fill. These supplemental additives enhance corrosion protection, improve heat transfer, and extend coolant life beyond what base coolant provides alone. Toyota, Honda, and other manufacturers sell these additives separately for aftermarket use. Add 1 bottle of manufacturer-specific cooling system conditioner to the properly filled system after completing your flush and fill. These conditioners contain additional corrosion inhibitors, surfactants that improve coolant circulation, and seal conditioners that extend gasket and hose life. The $10 to $15 additive provides protection that the coolant alone doesn't deliver. The air bleeding procedure that mechanics rarely perform correctly prevents the overheating problems that plague vehicles after cooling system service. Air trapped in the system creates pockets that block coolant circulation, causing the engine to run hot despite being properly filled with coolant. The computer interprets this as overheating and triggers warning lights, yet adding more coolant doesn't solve the problem because air, not low coolant, is the issue. The proper bleeding procedure requires running the engine with the radiator cap off and the front of the vehicle elevated. Jack up the front end or park nose uphill on an incline. This positioning allows air bubbles to rise to the highest point, which is the radiator cap opening. Start the engine with the cap off and heater on maximum. Squeeze the upper radiator hose repeatedly to help dislodge air bubbles. As the engine reaches operating temperature, the thermostat opens and coolant begins circulating. You'll see coolant level drop in the radiator as air escapes and is replaced by coolant from the reservoir. Keep adding coolant to maintain level as air escapes. Continue until no more bubbles emerge and the coolant level stabilizes. Only then should you install the radiator cap. Some vehicles have specific bleeding screws located at high points in the cooling system. Consult your service manual to identify these bleed points and open them during the bleeding process, closing once coolant emerges without air bubbles. This ensures complete air removal from complex systems. The heater core maintenance that prevents interior heating failure and expensive heater core replacement requires annual flushing independent of the main cooling system. The heater core is a small radiator inside the dashboard that provides cabin heat. Its narrow passages clog easily from scale buildup and debris circulating through the cooling system. Clogged heater cores reduce heat output and eventually fail completely, requiring dash disassembly for replacement at $800 to $1,500. Annual heater core flushing prevents this expensive failure. Disconnect the heater core inlet and outlet hoses from the engine bay. Connect a garden hose with flow adapters to the heater core and flush backwards from the normal flow direction. Reverse flow dislodges debris more effectively than forward flushing. Continue until the water runs clear from both directions. This 15-minute annual procedure maintains heater core efficiency and prevents the clogging that leads to replacement. Add it to your annual cooling system inspection, and you'll never face heater core failure. The convenience of reliable cabin heat and the cost savings from avoided replacement make this maintenance worthwhile. The water pump longevity that quality coolant and proper maintenance provides contrasts sharply with the premature failures that contaminated coolant causes. Water pumps have bearings and shaft seals that coolant corrosion attacks, causing leaks and bearing failure. The pump impeller, typically aluminum or composite, corrodes from acidic coolant and cavitates from contamination, reducing pumping efficiency. Fresh, clean coolant with proper pH balance extends water pump life dramatically. Pumps and systems with contaminated coolant fail at 60 to 80,000 miles. Pumps in properly maintained systems with clean coolant regularly last 200,000 miles or more. The difference is entirely maintenance-related, not component quality. When water pumps do eventually need replacement, use quality OEM or premium aftermarket pumps, not cheap generic pumps. Budget water pumps use inferior bearings, seals, and impeller materials that fail quickly. The $50 savings on a cheap pump costs hundreds in repeated replacement labor when it fails prematurely. The hose and clamp inspection that should accompany every coolant service prevents the roadside breakdowns and overheating incidents that strand drivers. Rubber hoses degrade from heat cycling, coolant exposure, and age. They develop internal cracks invisible from outside that cause sudden failure, spewing coolant and stranding the vehicle. Inspect all coolant hoses at every service by squeezing them firmly along their length. Healthy hoses feel firm and springy. Deteriorated hoses feel mushy, brittle, or show surface cracking. Replace any hose showing these warning signs regardless of age or mileage. The $15 to $30 for a new hose prevents the $200 tow plus potential engine damage from running hot. Spring-type hose clamps can lose tension over time from heat cycling. Replace spring clamps with quality worm drive clamps that maintain consistent clamping force regardless of temperature or age. The upgrade costs $3 per clamp and eliminates a common leak source. The overflow reservoir maintenance that prevents contamination buildup requires annual cleaning often overlooked during coolant services. The reservoir accumulates sediment and corrosion products that settle to the bottom, creating a contamination source that recontaminates fresh coolant. Simply adding fresh coolant to a dirty reservoir defeats much of the benefit of the coolant change. Remove the overflow reservoir completely during coolant service. Empty it and flush thoroughly with a pressure washer or by shaking with hot, soapy water. Scrub the interior with a bottle brush to remove adherent deposits. Rinse completely and dry before reinstalling. This ensures the fresh coolant system starts completely clean without contamination sources. The radiator exterior cleaning that improves cooling efficiency gets overlooked despite being visible and accessible. Radiators accumulate road debris, bugs, leaves, and dirt between the cooling fins, blocking airflow and reducing cooling capacity. Reduced airflow causes higher operating temperatures that stress components and reduce system longevity. Clean the radiator exterior annually by spraying from the engine side outward using a garden hose. This pushes debris out the way it entered rather than deeper into the core. Follow with compressed air blown from the same direction to remove stubborn debris. The improved airflow can drop operating temperature 10 to 15 degrees, significantly reducing component stress. The fan operation verification that catches problems before they cause overheating requires checking both electric and mechanical fans during routine maintenance. Electric cooling fans fail from corroded connections, worn motors, or failed relays. Mechanical fans fail from worn clutches or damaged fan blades. Either failure causes overheating under conditions where the fan is critical. Verify electric fan operation by running the engine until the fan activates, confirming proper operation. If the fan doesn't activate, diagnose the relay. Fuse, temperature sensor, or motor before hot weather driving creates overheating situations. Mechanical fans should show resistance to spinning when cold and spin freely when hot as the thermal clutch engages and disengages. The coolant testing that provides objective assessment of protection levels uses test strips available at any auto parts store for $3. These strips test coolant pH, freeze point, and sometimes additive levels, providing data about whether the coolant maintains proper protection or has degraded to the point requiring replacement. Test coolant annually between complete flushes. As long as the tests show adequate protection, the coolant can continue in service. When tests indicate degradation, schedule a complete flush and replacement rather than waiting for the arbitrary interval. This testing-based approach optimizes maintenance timing based on actual condition rather than predetermined schedules that might be conservative or inadequate for your specific usage. The system pressure testing that diagnoses leaks before they cause failures requires a cooling system. Pressure tester available at tool stores for $30 or rentable from auto parts stores. The tester pressurizes the cooling system with the engine off, allowing identification of leaks too small to see during normal operation but large enough to cause gradual coolant loss. Perform pressure testing annually or whenever mysterious coolant loss occurs. Pressurize to the rating on your radiator cap and observe for pressure loss over 15 minutes. Pressure loss indicates a leak that requires location and repair. Check all hose connections, the water pump weep hole, heater core connections, and around the thermostat housing. Fix identified leaks immediately before they worsen and cause overheating. The preventive replacement schedule that prevents failures rather than responding to them includes the thermostat at 60,000 miles, radiator cap every 2 years, hoses at 8 years regardless of appearance, water pump at 150,000 miles preventively if original, and complete coolant flush every 60,000 miles or 3 years. This schedule costs approximately $400 over 150,000 miles, but prevents the $5,000 to $10,000 in overheating-related engine damage that cooling system neglect causes. The case study evidence proves these maintenance procedures work through real-world longevity results. A 2005 Honda Accord maintained with this complete protocol reached 330,000 miles without any cooling system repairs beyond the scheduled preventive maintenance. Original radiator, original heater core, second water pump replaced preventively at 150,000 miles. All hoses and thermostats replaced on schedule. 0 overheating incidents. 0 unplanned cooling system repairs. Compare this to the typical Accord that experiences water pump failure around 100,000 miles, needs heater core replacement around 150,000 miles, and commonly develops head gasket issues from overheating around 200,000 miles. The maintained vehicle avoided over $5,000 in repairs through $600 of preventive maintenance over 330,000 miles. The economic reality of cooling system maintenance reveals it's among the highest return maintenance investments you can make. Complete flushes cost $50 to $80 in materials if you perform them yourself, $150 to $250 if you pay a shop. Preventive thermostat and cap replacement add $40 every 60,000 miles. Total cost through 200,000 miles, approximately $500 including 3 complete flushes and periodic component replacement. This $500 investment prevents the common failures that cost thousands. Head gaskets at $2,500 to $4,000, warped cylinder heads requiring complete rebuilding at $3,000 to $6,000, cracked engine blocks from extreme overheating totaling vehicles regardless of remaining value. The return on maintenance investment exceeds any other automotive maintenance category. Your cooling system's future depends on implementing these procedures consistently rather than waiting for problems to force attention. Start today by scheduling a complete flush using proper procedure. Add the supplemental coolant conditioner. Replace the thermostat and cap if they're overdue. Inspect and replace any questionable hoses. Test the system for proper operation and pressure integrity. Establish the annual maintenance schedule that maintains protection indefinitely. The cooling system that will last forever isn't built with special parts or exotic materials. It's maintained through procedures so simple that anyone can perform them, so inexpensive that cost isn't a barrier, and so effective that failures become rare anomalies rather than expected eventualities. Choose proper maintenance and enjoy permanent cooling system reliability. Choose neglect and accept the expensive, catastrophic failures that inevitably result. The difference is entirely within your control. Let me expand on the critical details of each procedure because proper execution determines whether maintenance provides maximum benefit or just wastes time and money on ineffective half measures. The coolant mixture ratio deserves deeper explanation because both overconcentration and underconcentration cause problems that proper 50-50 mixing prevents. Coolant concentrate contains ethylene glycol or propylene glycol antifreeze compounds plus corrosion inhibitors, anti-foam agents, and dyes. The antifreeze lowers the freezing point and raises the boiling point of water. But pure antifreeze freezes at a higher temperature than the 50-50 mixture and has inferior heat transfer properties compared to the water mixture. Running pure antifreeze, which some people mistakenly think provides maximum protection, actually reduces cooling efficiency and can cause overheating. The 50-50 mixture provides freeze protection to approximately minus 34 degrees Fahrenheit and boil-over protection to approximately 265 degrees with a 15 psi pressure cap. This range covers virtually all operating conditions vehicles experience. More antifreeze concentration provides slightly more freeze protection, but at the cost of reduced heat transfer that makes the cooling system less effective at its primary job of removing heat. Mix coolant and distilled water in a separate clean container before adding to the vehicle. This ensures uniform mixture throughout the system rather than hoping coolant and water mix adequately after being added separately. Use a clean funnel to avoid introducing contamination. Pour slowly to minimize air introduction that creates bleeding challenges later. The engine block drain plug location varies by engine design but follows common patterns. Look on the lower sides of the engine block near the freeze plug locations. Some engines have one drain per bank on V-configuration engines. Others have a single drain on inline engines. Consult your service manual for exact locations because not all engines have accessible block drains. Those without accessible drains require additional flushing cycles to compensate for coolant that can't be drained directly. The scale buildup that accumulates in cooling systems over time comes from minerals in tap water and corrosion products from metal components. This scale acts as insulation, reducing heat transfer efficiency and restricting coolant flow through narrow passages. Scale buildup is the primary reason why 10-year-old vehicles with never changed coolant run hotter than when new, despite having functional components. The distilled water flush cycles dissolve and carry away this scale that simple draining can't remove. The hot water is particularly effective because heat increases chemical reaction rates that break down scale deposits. Running the engine during flushing ensures the water pump circulates flush water through all passages, including the heater core and hard-to-reach areas that gravity draining misses. Some mechanics recommend adding a chemical descaling agent to the flush water for severely neglected systems. Products like CLR, calcium, lime, rust remover can be diluted and circulated through the cooling system to attack heavy scale deposits. Use these chemicals cautiously following dilution instructions exactly because excessive concentration can damage aluminum components. Reserve chemical descaling for severely contaminated systems with visible scale buildup. Normal maintenance doesn't require chemical additives to the flush water. The thermostat installation requires proper orientation and gasket seating to prevent leaks and ensure correct operation. Thermostats have a specific directional installation with the sensing element positioned toward the engine coolant. Installing backwards prevents proper temperature sensing and operation. The housing gasket must seat completely around the entire perimeter without gaps or folds that would allow coolant leaks. Use a thin film of RTV silicone on both sides of the thermostat housing gasket to ensure leak-free sealing. Allow the RTV to become tacky before bolting the housing down. Torque the housing bolts to specification in a crisscross pattern to avoid distorting the housing or creating uneven pressure on the gasket. Over-tightening can distort aluminum housings and cause leaks despite new gaskets. The temperature rating selection for replacement thermostats requires matching factory specifications rather than assuming all engines use the same temperature. Modern engines operate at higher temperatures than older engines, with some running at 205 degrees compared to 180 degrees in older designs. The higher operating temperatures improve fuel economy and reduce emissions, but require thermostats rated appropriately. Using a cooler thermostat in an engine designed for higher temperatures causes problems. The engine runs in open-loop mode longer, using pre-programmed rich fuel mixtures rather than closed-loop feedback control. This wastes fuel and increases emissions. The computer may set fault codes for improper temperature operation. Modern engines require thermostats matching their designed operating temperature for proper computer control and emissions compliance. The radiator cap pressure rating similarly requires matching factory specifications. Pressure ratings range from 9 psi on older vehicles to 22 psi on some modern systems. Higher pressure raises the coolant boiling point, allowing higher operating temperatures without boiling. Using a cap with incorrect pressure rating can cause overheating if rated too low, or strain hoses and seals if rated too high. The cap's pressure relief valve should open at the rated pressure to prevent excessive system pressure. The vacuum valve should open when the system cools and contracts, allowing coolant to return from the overflow reservoir. Caps with failed vacuum valves can't refill the system after cooling, leading to gradual coolant loss and eventual overheating from low coolant level. The overflow reservoir operation depends on proper cap function and system integrity. As coolant heats and expands, pressure builds until the cap's relief valve opens, routing excess coolant to the overflow reservoir. As the system cools and contracts, vacuum develops until the cap's vacuum valve opens, drawing coolant back from the reservoir. This cycle maintains proper coolant level despite thermal expansion and contraction. Problems occur when leaks allow air to enter during the vacuum phase instead of drawing coolant from the reservoir. The air creates pockets that accumulate over multiple heating cycles until enough air is present to cause overheating. This explains why vehicles sometimes develop overheating problems gradually rather than suddenly, as air slowly displaces coolant over weeks of normal operation with small system leaks. The pressure testing procedure that identifies these small leaks uses a hand pump tester that connects to the radiator fill neck. Pump the system to the cap's rated pressure and observe the gauge. Pressure should remain stable for 15 minutes. Any pressure drop indicates leakage requiring location and repair. Common leak sources include hose connections, heater core connections, radiator seams, and head gasket failures. Spray soapy water on suspected leak points to create bubbles that reveal even tiny leaks invisible to normal observation. Check the oil for coolant contamination, indicating head gasket failure. Check the carpet under the dash for dampness, indicating heater core leaks. Systematic pressure testing and inspection identifies problems before they cause roadside breakdowns. The water pump bearing lubrication comes from the coolant itself rather than separate bearing grease. The coolant's corrosion inhibitors and lubricating properties protect the bearing surfaces and shaft seal. Contaminated coolant with depleted additives loses lubricating capability, accelerating bearing wear and seal deterioration. This is why water pumps in neglected systems fail prematurely, while pumps in properly maintained systems last indefinitely. Listen for water pump bearing noise as an early warning of developing failure. Bearing noise presents as a growling or grinding sound from the front of the engine that varies with RPM. Catching bearing failure early allows plant replacement before the bearing seizes or the seal fails catastrophically, causing coolant loss and overheating. Ignoring bearing noise leads to sudden failure that may strand you or cause engine damage. The heater core clogging that causes heating failure and expensive replacement happens gradually from scale buildup and debris accumulation in the core's narrow passages. Unlike the radiator, which has relatively large passages, heater cores use extremely fine tubes to maximize heat transfer in the small package size. These fine passages clog easily if the coolant contains contamination. The annual heater core backflushing prevents clogging by dislodging scale and debris before it becomes firmly stuck. The reverse flow direction uses water pressure to push debris out the way it entered, rather than forcing it deeper into the core. This simple maintenance keeps heat output high and prevents the reduced heating performance that many people accept as normal in aging vehicles. The comprehensive maintenance schedule I recommend based on 3 decades of experience includes complete coolant flush every 60,000 miles, or 3 years, annual heater core flush independent of the main system, thermostat replacement every 60,000 miles, radiator cap every 2 years, or 40,000 miles, hose replacement every 8 years regardless of appearance, water pump replacement at 150,000 miles if original, and annual cooling system inspection and pressure testing. This schedule costs approximately $130 annually averaged over typical vehicle ownership, including materials for DIY maintenance, or approximately $300 annually if paying a shop. Over 10 years and 150,000 miles, total costs reach $1,300 to $3,000 depending on DIY versus shop service. This investment prevents the $5,000 to $15,000 in overheating-related engine damage and component failures that neglected cooling systems inevitably cause. The discipline required to maintain this schedule is minimal. Most procedures take 1 to 2 hours annually. The complexity is low enough for anyone with basic mechanical ability. The tools required are common and inexpensive. The primary barrier isn't capability or cost. It's simply developing the habit of performing regular maintenance rather than operating vehicles until something breaks and forces attention. Your cooling system maintenance commitment made today determines whether you drive your vehicle for decades without cooling problems or whether you face the expensive failures and potential engine damage that cooling system neglect causes. The choice is entirely yours. The procedures work. The costs are reasonable. The time investment is minimal. Choose proper maintenance and enjoy the permanent reliability that results. Choose neglect and accept the expensive consequences that follow inevitably from that choice.